Hello everyone. I am G.J.L from the Department of Mechanical Engineering, University of Peradeniya. Today I will be presenting the progress on my final year individual research project. The title of my research is Comparison of Energy and Water Consumption in Air-Cooled and Water-Cooled Condensers for Small Steam Power Plants. As the global energy landscape shifts toward resource efficiency, evaluating the trade-offs between these two cooling technologies is important. The main aim of this study is to evaluate and compare the performance of air-cooled and water-cooled condensers under high ambient temperatures, particularly in Sri Lanka. Additionally, I aim to identify optimization methods to improve performance and efficiency of both condenser types under elevated ambient temperatures between 30 to 40 degrees Celsius. This shows the timeline of the first phase of my research. As you can see, currently I am in the 10th week and I tried my best to follow this timeline so far. I was able to do the foundational literature review and prepare an implementable project plan. My research methodology is structured in 4 key stages. As I have completed the literature review, now I am moving toward the second stage. Here, I will collect real-world plant operational data of air-cooled and water-cooled condensers for a comprehensive analysis of their performance. Now, let's see what I found through my literature review. From the literature review, some clear trends have been identified. Power plants using air-cooled condensers suffer a 5 to 10% plant-level efficiency penalty compared to plants with water-cooled condensers. This highlights the core problem my study addresses. Also, this vulnerability is a major challenge for implementing air-cooled condensers in a tropical country like Sri Lanka, where high temperatures are the norm, and it is what makes this comprehensive study so important. Furthermore, there is a massive gap in capital investment. Air-cooled condensers can cost approximately 3.5 to 5 times more than water-cooled condensers in terms of installation and operational infrastructure. This is because air-cooled condensers have large heat exchangers, huge fin areas, and additional support structures. High initial cost is a major barrier to the adoption of air-cooled condenser technology, even though it reduces water consumption significantly. Let's see what are the other challenges towards air-cooled condensers. Air-cooled condensers suffer a performance penalty relative to water-cooled condensers due to the very poor thermal properties of air. Air-side heat transfer coefficients are much lower than values for evaporative side heat transfer coefficients of water-cooled condensers. Because of the thermal barrier, air-side thermal resistance dominates 96% from the total thermal resistance. Atmospheric pressure, air has a very low volumetric specific heat capacity compared to the water. Therefore, it is necessary to supply more air than water to provide the same thermal capacity for heat removal from the condenser, which is accompanied by a large fan power requirement. As an example, if we consider a steam condensation temperature of 37 degrees Celsius, this results in an efficiency of just 26% for an air-cooled condenser compared to 63% for a water-cooled condenser. This difference results in air-cooled condensers requiring a higher initial temperature difference. Temperature difference means the temperature difference between inlet steam and inlet air. Because of the high thermal resistance, higher temperature difference is needed to drive the heat transfer process. As I previously said, this needs large fan power requirement, leading to higher auxiliary power consumption. Further, because we need so much surface area to exchange heat with air, air-cooled condensers require a large land footprint. Air-cooled condensers are generally placed 20 to 50 meters above ground level, and they are enclosed by wind poles to reduce the impact of wind and potential air recirculation. Therefore, a strong, expensive support structure is needed to hold all that weight. On the other hand, if we increase initial temperature difference, that means we are increasing the turbine back pressure. It lowers the power generation capacity. Therefore, this is only advantageous up to the point where the benefits from heat exchange enhancements are offset by increased auxiliary power and capital costs. Operation of the air-cooled condensers is highly dependent on environmental conditions. When the ambient temperature increases, air-cooled condensers become more inefficient, and that's why we need to find solutions. Also, solar radiation and wind decreases the efficiency. To mitigate these issues, literature suggests several enhancement techniques. These include the use of ringlet vortex generators and passive chaotic mixing to improve the airflow. I am also looking into methods like air jet impingement, mechanical mixing, and advanced techniques such as electrohydrodynamic and acoustic enhancement. Here is the most critical gap I have identified in the literature. Most existing studies on condenser performance are conducted at ambient temperatures around 30 degrees Celsius. However, in Sri Lanka, ambient temperatures often range between 30 and 40 degrees Celsius. My research aims to directly investigate how both condensers perform and how their energy and water usage profiles change, specifically within this high temperature window that is so relevant to our local context. Additional gaps include the lack of life cycle cost models that include both capital and operational costs. There is also a need for reliable methods to save both water and energy under high ambient temperatures. Further, climate resilience analysis and a practical condenser selection guide are lacking in literature. If I come back to the timeline, I try to collect real-world plant operational data in the upcoming weeks. Here, I have faced a challenge to find an air-cooled condenser in Sri Lanka. Finally, I heard that the Karavalapitiya waste to energy 10 megawatt power plant has an air-cooled condenser. Therefore, I am planning to visit there in near future. These are some key references used in my literature review. Special thanks goes to my project supervisor, Miss L.U. Peradeniya, and the staff of Vitul Lanka's Dendro Power Plant in Deyathagandi. That's all for today. Thanks for watching.